Hello and welcome. Today we're going to be discussing the problem chip exchange from the first 2026 USACO bronze contest. In this problem, we are given two types of chips. We are given A copies of chip type A and B copies of chip type B. And we have the ability to turn B chips into A chips, and we are given values CB and CA that describe a ratio. So every CB copies of B chips can turn into CA copies of the A chips. And we want to determine the minimum value X such that receiving X new chips will always result in at least F of A chips. So F of A, it's some objective. We don't necessarily have that many A chips at the beginning, but we want to be able to reach that. And we want to know what is the minimum value of X to guarantee that we can always achieve this F of A value. So we want to think of this problem in adversarial terms, sort of like what is the worst case scenario? What are the worst chips I could get that's going to take as long as possible to reach this FA goal? So on the left-hand side of the screen here, I have an example with the different parameters we might have. So just to recap here, the values A and B are going to be giving us the initial amount of each chip type. CA and CB give us the exchange ratio. So if CA is 2 and CB is 3, that means every 3 B chips will produce 2 A chips. And then the final value here, F of A, this is how many A chips we want to produce. So we currently have 6, but we want to reach 14. So to start off this process, one thing we can do is we can turn all of the available B chips into A chips. So for example, here we can select these 3 B chips, we can delete them, and that is going to produce 2 A chips because every 3 B chips can be turned into 2 A chips. So now we're at 8 A chips in total, and in order to reach that, we consumed 3 B chips. And we can do that again, deleting another 3 B chips, and then we are going to produce another 2 A chips. So now we're at 10 A chips. And the question here is sort of what is the worst way to produce more A chips? One method of producing more A chips is just to give myself more A chips, right? I could just copy and paste and give myself a bunch more A chips until eventually I reach 14. And that would require giving myself 4 more chips. However, if we take a look at the exchange rate between A chips and B chips, we can see that it requires more B chips to produce an A chip. So it might be a slower path to give myself B chips instead. And when I say slower, I mean requiring more chips. So if I instead choose to give myself 3 copies of the B chip, or let's say 2 copies of the B chip. So we're going to start with 2 copies of the B chip. Those 3 B chips that are now in the B chip collection can be transformed into 2 A chips. So I'm going to give myself 2 A chips. So I've given myself 2 B chips, and that's produced 2 A chips. I'm then going to give myself 1 more A chip. And the reason why I want to give myself 1 more A chip here is that would put me exactly at 13 A chips. And that is 1 smaller than the amount I need. So far, just to keep track of what we have done here, we have given ourselves 2 B chips, and we've given 1 A chip. The idea behind the B chips is it's slower to produce A chips using B chips, so that's the optimal strategy. And the idea behind this singular A chip is giving myself this 1 A chip is not helpful. right? It hasn't allowed me to reach my target. And the next copy of 3 B chips that I give to myself is going to boost me over that limit anyway, right? If I go from 12 to 14, I've reached the goal. If I go from 13 to 15, I've still reached the goal. So once I get close to the goal, I want to get as close to the goal as possible without going over. And then I want to produce the remaining A chips using the B chip exchange because again, I have to give a lot more B chips to create the equivalent amount of A chips. So what I'm going to do is I'm going to give myself another 3 B chips. And in doing so, that's going to produce 2 more A chips. And I'm going to arrive at a total of 15 A chips. And that has finally met or exceeded the goal of 14 A chips. So we can see that in order to reach at least 14 A chips using this distribution required 6 chips to be given. And this is sort of the worst case scenario, right? The idea here was that the B chips were bad at generating A chips, so I wanted to generate lots of B chips because that's slow. And then also I could sneak in this 1 A chip here because it wasn't helpful in reaching the goal, right? To have 1 extra A chip at the end didn't actually help me. So what we're going to see is that in this problem, there are actually 2 cases, or at least 2 major cases. The first case is that C of A is less than C of B. This is the case that we analyzed here to the left. And in this case, it is better on average to create B chips. So the rough idea of what we want to do for the worst case scenario is we are going to generate lots of B chip and then we're going to generate just enough A chips to be unhelpful. And we're going to define what unhelpful means later on. On the other hand, if C of A is greater than C of B or equal to it, then creating a B chip is actually the same as creating an A chip or potentially even more helpful, right? 1 B chip could turn into multiple A chips. So we're going to want to, for the most part, avoid creating B chips. So in this case, the worst case scenario is we are going to generate lots of A chips. And then again, we're going to try to generate just enough B chips to be unhelpful. I think that this case is actually a little bit easier to analyze. So we're going to start off with this case. So what does it mean to generate lots of A chips? Well, the key idea is that A is the amount of A chips I currently have. F of A is the amount of A chips that I want. So the amount of chips that it would take if I was just generating A chips to get from A to F of A is the difference between those two. So the amount of new A chips I need is simply F of A minus A. This problem, as you can suspect by the input sizes, is going to require a lot of math formulas, right? What we're doing here is we are generating math formulas to address all of the cases in the problem. So this question, very little coding, almost entirely math. Now let's think about what does it mean to generate enough B chips to be unhelpful? Well, when do the B chips help us? The B chips help us when we reach this value C of B, right? Because once we reach the value C of B, we can transform this pool of B chips into A chips. And that's very helpful, particularly when C of A is bigger than C of B. So what we're going to do for the B chips is we are going to produce just enough new B chips to stay right under C of B. So we're currently at B chips, and we are going to add some new B chips so that the total amount of B chips is exactly C of B minus 1. And the benefit of this is we are left over with this large pool of B chips that can't be used to create A chips. So this is sort of the idea of approaching the question from an adversarial perspective. What is the worst thing that could happen to me? Well, the worst thing that could happen to me is I have all of these B chips that I can't use. So when I want to know how many chips do I need to guarantee F of A when this condition is true, well, it's just going to be the sum of these two values. These A chips are going to allow me to reach f of a, and these B chips are going to be some extra spares that are actually unhelpful in reaching f of a. And then there's the same sort of analysis for when C of A is less than CB, but it's just a little bit more complicated because I'm going to be transforming B chips into A chips. So my path to actually reaching F of A is a little bit more complex. So we're going to take a look at this formula here and break it down. So the first part, which is the easiest part, is this minus B. This minus B just represents the amount of B chips I already have. So if I start with some amount of B chips, those are going to help contribute to reaching the next copy of C of B. So now let's talk about what's happening over here. The first thing we can notice is this f of a value. So this f of a is just the amount of chips I need. And what we're trying to do here is count how many copies of CA do I need to obtain in order to reach f of a. So the key idea is this is the amount of chips I need, and then I'm dividing it by C of A. Why we are adding C of A plus 1, or sorry, C of A minus 1 here, this is just to round up. So the key idea, what we're really looking at here is simply the ceiling of f of A minus A divided by C of A. So this extra plus CA thing, it looks a little confusing, but this is just a trick that's allowing me to round up instead of round down in my division. So this is going to give me exactly how many copies of C of A I need in order to reach my target. And then once I have this value, the question is, how many B chips will that cost me? Well, each copy of C of A requires me to consume CB chips of type B. So if I need this many sets of CAA chips, the total cost in the number of B chips will be C times B, or CB times this value. So this is how many sets of CA I need, and then I'm going to multiply by the number of B chips that each set requires. So this is how many B chips I need to reach the goal FA, and this is how many B chips I already have. So the difference between those is going to be the value of new B. The last part here, which is maybe the trickiest, is this idea of generating just enough A chips to be unhelpful. And that's where we add in this formula. So what's happening here? As we saw in the example to the left, we were able to sneak in this one extra A chip because every time we created a set of CA chips, that was adding a factor, or that was adding 2 new A chips. So if the amount I wanted to reach was some even value and I kept on adding 2s, I could go one below that, one below the objective, and then force myself to actually go over the objective. So what's happening here is this is calculating the maximum number of A chips I can give myself without reducing the number of sets of CA I require. So this is like, how close can I get to a full set of CA without actually producing a full set of CA? Because if I actually produce a full set of CA, then this would reduce by 1, and therefore I'll require less B chips. So I'm giving myself just enough A chips to not change the outcome. And again, we're thinking about this from the adversarial perspective. What is the worst thing that can happen to you? And the worst thing that can happen to you is that the number of A chips you end up with is actually more than you needed. So in these two cases, what I want to do is first determine which case I'm in, and then simply return the sum of the number of new A chips and new B chips I have. There is one extra thing that we have to watch out for, and it is possible that at the very beginning of the example, when I converted all, let's go back in our example to the very beginning, the initial setup here. It is possible that when I converted all of my B chips into A chips at the beginning, I just reached my objective. So imagine my objective here was actually much smaller. Let's say my objective was I wanted 8 A chips. Well, when I started by converting all of my B chips to A chips, you can see that I actually instantly hit that goal. So the extra thing that we're going to have to check for is if we've just hit the goal while converting the initial amount of chips we started with, then it is possible that we won't need to add any more chips. And in that case, we will just return 0. So if at any point before we start adding chips, A is at least the goal, then we just have to return 0. We don't need any extra chips. We've already hit the goal. So with that sort of analysis of that case out of the way, let's try to write the code. Again, the code here is going to be pretty short because the code is just implementing these formulas. The hard part of the question is coming up with these formulas. Note, this question has a lot of opportunities for partial credit, particularly if you avoid math formulas, right? You can do a lot of this with simulation and trying different combinations of A chips and B chips. So if these math formulas are not your strong suit, what I'd recommend on the contest is spend very little time on this question, focus on the other two questions, and then come back on the end of the contest to try to get as much credit on this question as possible. So note that even though this is problem 1, doesn't mean that necessarily this is the first problem you should solve. Different problem solving styles will find this question easy or difficult. If you have a really strong math background, this question might be extremely easy for you. If you don't have a really strong math background, this might have been the hardest question on the exam. So again, just keep in mind everyone has a different problem solving style. Anyway, let's take a look at the code. So we're going to start here by first taking all of the B chips we have and converting them into A chips. So we're going to see how many sets of B chips do I have? And for each set of those B chips, I'm going to get CA copies of A chips. And then the remaining B chips is whatever my remainder is after dividing B by CB. For those of you who are coding in Java and C++, note that double slash in Python just means a single slash in C++. So this just means division rounded down. So if you see double slashes here, note that this is just normal division as it would operate in Java and C++. Next up, we have our first case. And that first case is the edge case where we just already have enough A chips. So that is checked with if f of A is smaller or less than or equal to A. If that is true, we just return 0. We don't need any more chips. Otherwise, we have to check which case are we in. Do we want to generate A chips or do we want to generate B chips? So here, if C of A is greater than C of B, the optimal strategy is to generate primarily A chips. And so the new A is going to be f of A minus A, right? Every time we add an A chip, that's just one more A chip in our collection. So we can add a maximum of f of A minus A chips. And then we add just enough new B chips to be unhelpful, right? Just enough to not reach this value of CB. And then next up, we return the sum of those two things. On the other hand, if it is better to generate B chips, then we are going to generate just enough A chips to be unhelpful. And then we're going to primarily generate the rest of our chips using B chips. And we're going to sort of do the exact same thing here, but we just account for that conversion ratio, right? You can see, again, we're primarily adding f of A chips, but then we're multiplying by this conversion ratio, which is going to be harmful to us in the sense that it's going to require us to use more chips to get to our goal. And then we, of course, have to remember to subtract off the amount of B chips we already have, just like we did in the other case. And that's pretty much it. We return new A plus new B, run the code, and it works perfectly. So as you can see, very mathy question. You can solve it in very few lines of code if you condense everything down, but hopefully this format is a little bit more readable. Anyway, thank you so much for watching the video. I'll catch you in the next one. Have a wonderful day, and bye-bye.